I will present some technical tools for the calculations in triangulated categories, which are related to matrix problems, namely to bimodal categories. Applying this technique to the stable homotopy category, we obtain a complete classification of stable homotopy types of polyhedra having cells at most in 4 successive dimensions, and of torsion-free polyhedra having cells at most in 7 successive dimensions. These results were mainly obtained in collaboration with Hans-Jürgen Bauers, and for details you can see my papers, my surveys. Yeah, I must say that these results are not very new, but as far as I know, they are not so known, especially for topologists. So I decided to present them here. Okay. Now, this is content. First, I will say several words about stable homotopy categories, then go to general construction, and then consider the categories I was speaking about. By what I denote the homotopy category of pointed Hausdorff spaces. Thus, what I said is a set of homotopy classes of maps which preserve fixed points. By x, v, y, I denote the wedge or bouquet of x and y, that is the subspace of, and by x till y is smash product. That is the quotient of the direct product by bouquet. In particular, I consider cone of over x and suspension of x. Yeah, the suspension can be presented by this picture. We take x, take this thing, and then make all this wavy edge 1 point. Yeah. Okay. The suspension is a functor, so we have a sequence of natural maps from homotopy classes from x to y, then to sx to sy, s square x, s square y, and so on. And we consider the direct limit. Yeah, we call this set of stable homotopy classes of maps from x to y. Thus, we obtain this stable homotopy category HOS. Yeah. This category has several convenient advantages. First of all, the sets, the morphism sets are abelian groups. Yeah, so this is an additive category. The direct sum is just bouquet. Moreover, it is a triangulated category, yeah, where the shift is just suspension. It means that we could fix exact triangles, which are cofibration sequences like this, and sequences isomorphic to cofibration sequences. Yeah. Here, CF is the cone. Maybe I will show the picture. If we have a morphism from x to y, then we take the cone over x, then glue it to y using this morphism f on the bottom, and then we just take quotient by y, yeah, so map y to the unique point, then we take the suspension. An important feature of triangulated category is the following. If we have an exact triangle, then for every object A, there are exact sequences of groups like this, which are infinite. Yeah. And it gives the following possibility to construct new object or new stable homotopy types in our case. Let A and B be additive subcategories of some triangular category. For instance, of the category of stable homotopy category. Usually they are not triangular subcategory. They are not closed under shifts under suspension. Yeah. And then I denote by this A cross B, the subcategory consists of all object C, which can be included in the equifibration sequences, which are cones of morphism from A to B, where A is from A, B from B. Yeah, and consider the functor from A and B to abelian groups, which is contravariant by A, covariant by B, and just this set of morphisms from A to B. Then we can define the bimodal category of this bimodal, of this functor. Its objects are all morphisms from A to B, yeah, where A run through A, B run through B. And morphisms, if we take F and F prime, a morphism is just a pair, alpha, beta, yeah, such that this diagram is commutative. For every, we can do the following. For every F, for every object of our category, we fix an exact triangle. And if alpha beta is a morphism from F to F prime, yeah, there is a commutative diagram. This is a property of triangulated category. So we always have a morphism from C to C prime, such that the whole diagram is commutative. Yeah. Usually gamma is not uniquely defined. And moreover, if we have gamma from C to C prime, we cannot assert that it occurs in such a diagram. And even if it does, we cannot assert that alpha and beta are uniquely defined. Nevertheless, under some conditions, we can state that each gamma arises from some alpha beta, and conversely, and we can control the lack of uniqueness. Namely, we suppose that there are no morphisms, non-zero morphisms from objects from B to suspensions of objects from A. So no morphism, for instance, from B to SA prime. Then, if we have this gamma from C, if we have these two exact triangles and have gamma from C to C prime, then this product, H prime gamma going this way, is zero. It is a map from B to SA prime. Hence, gamma gamma G, this can be factors through B prime. It equals G prime beta for some beta. Now look, we have exact triangles, we have commutative diagram, this one, so it can be extended to the big commutative diagram, so we have alpha also, and such that the whole diagram is commutative. Now about non-uniqueness. So certainly we must trace it only for gamma when a gamma is zero. If gamma is zero, are alpha and beta also zeros or not? Certainly not. If gamma is zero, then this product gamma G, G prime beta, is zero. Yeah. So beta can be factored through A prime, through F prime. Just in this way, S alpha factors this product, S alpha H is also zero. So S alpha can be factors through SF, through SB. And then order the same, since this suspension is an equivalence, alpha can be factored through F. Yeah. By the way, the same is true if gamma factors through any object from B, not necessary. Yeah, and as well as through some object of from suspension of subobject of A. In the same way, if alpha and beta are zeros, then gamma G is zero. So gamma is factored through H, yeah, through SA, and in the same way, gamma H prime gamma is 0, so gamma can be factored through B prime. So we have the following general theorem. We denote by I the ideal of this bimodal category, consisting of morphisms alpha beta, such that alpha factors through F and beta factors through F prime. Yeah. And denote by J the ideal of this gluing in B, consisting of such morphisms gamma that can be factors through an object of B and through an object suspension of sub-object of A. Then the construction above induces an equivalence of the quotient categories, this bimodal category by I and this gluing by J. Note that as we suppose that there are no morphisms from B to SA, this ideal is the square 0. So this quotient does not imply the isomorphic classes. And the isomorphic classes of these cones are the same as isomorphic classes of the object from the quotient category by model category by I. Unfortunately, I is not nilpotent, and here we must take quotient. We apply this theorem to the stable classification of CW complexes. We call them polyhedra, which have cells only in several successive dimensions, say D, D plus 1, and D in n successive dimensions. We denote this by CW Dn, starting from D and n successive dimensions. It is a subcategory of the homotopy category, consisting of this polyhedra. And moreover, the Freudenthal theorem implies that the suspension induces equivalences from D to D plus 1, such category if D is bigger than n. And if D equals n, it gives a one-to-one correspondence of isomorphic classes. So we consider the category with n successive cells and starting also from n. And we can consider it as a subcategory of a stable homotopy category, which doesn't matter. Now we construct these categories recursively, starting from n equals 1. Usually, of course, CW1, what does it mean? We have only one-dimensional cells. So this is just a bouquet of spheres. If n equals 2, then every object is either a sphere or a cone of morphism of spheres. Yeah? It is a gluing of a three-dimensional ball to two-dimensional sphere. Yeah? So it must be by map from the border. Yeah? But homotopy classes of morphism from S2 to S2 are just integers. Yeah, so F, this morphism F, can be considered as an integral matrix, and two such matrices give isomorphic cone if and only if one of them can be obtained from the other by multiplying by some invertible integral matrices. So we can now recall the Smith theorem about integral matrices, and it says that using this such transformation, we can make F diagonal. It implies that the cone of this morphism is actually a bouquet of Moore spaces, which are obtained by taking cones of each of these mappings, A1, A2, A3, and so on. Yeah. I recall that this Moore space is just a unique space that have only one non-zero homology group, namely in the dimension D. And it is a cyclic group of order A. For instance, this one, this is not a real projective plane. It is suspension of real projective plane, I beg your pardon. M2, the real projective plane has cells in dimension 1 and 2, and this one in dimension 2 and 3. Okay. Now, we can do the same for bigger n, and we use the following construction. We fix some integer, m, which is smaller than n minus 1, and consider the following categories. Maybe I will show them here. Our category has cells starting from n and up to 2n minus 1. Then B has cells starting from n up to n plus m, and A has cells starting from n plus m in up to 2n minus 2. This one. If X is in CWN, so if it has cells only on these levels, we can take its n plus mth skeleton. It belongs to B. And the quotient has cells only starting from the next one, n plus m plus 1, up to n minus 1. So it is a suspension of some object from A. Hence, there is a configuration sequence like this. And it means that we can identify our category with the gluing of A and B, with this A cross B. Note that these indices are smaller than n, so we may suppose that we already know the structure of these categories. And then we construct the bigger one. Following Bausch, we call it polyhedron from CWN and atom if it is indecomposable, so it is not of a wedge of non-trivial spaces, and does not belong to a smaller categories CW. It means that it has cells in both on the lower level and on the upper level, and maybe some cells in between. Okay. Obviously, every polyhedron is either an atom or a bouquet of atoms and maybe suspended atoms. For instance, the only atom in CW1 is the circle, and the atoms in CW2 are more atoms. And moreover, here we must have the power of prime number, because if A is B times C and the great common divisor of B and C is 1, then the Moore spaces corresponding to A is just the wedge of Moore spaces corresponding to B and C. So in the composable Moore spaces are only, we take only if here we have the degree of prime number. First, consider the first non-trivial case, n equal 3. Can we take m equal 1, then B, what is B? B is starting from 3 and have 2 levels. So it is just the same as, is the isomorphic to CW2. And A is starts from 4 and has only 1 level, so it is just consists of spheres. So in the composable polyhedron B are spheres and Moore spaces, and all objects of A are bouquets of spheres. Easy calculations using the presentation of Moore spaces as of cones give the following values of stable homotopy groups. That is, so for S3 it is a cyclic group of order 2. For S4 is just Z. For more spaces with odd degree, it is 0. And for even degree, it is again a cyclic group of order 2. The maps between these spaces map non-zero element of M4 to K to non-zero element of M4 to L if K is bigger to L. Yeah. So using automorphism of A and B, or bouquets of these spaces and spheres, one can reduce any map to a map presented by one of the following matrices. Either it is just PK from S4 to S4, or eta K. Eta K is the non-zero element of this group. Yeah. Or it can also be such that B consists of a sphere and this one, or S3, yeah. And the F maps, we have here 2 to L, and here we have eta. This one, PK, it sure gives more space, which is not an atom here. Yeah, because it has only 2 levels, and here we must have 3 levels. Yeah, the other matrices give the so-called chunk atoms. Yeah, we present them by their gluing diagrams following Bowers. They show which cells appear in these CVW complexes and how the bigger ones are attached to the smaller. For instance, here we have 5-dimensional cell, 3-dimensional space, and it is attached by using the map from, by using the Hopf map, eta, from 4-dimensional sphere to 3-dimensional sphere. Here we have more space, and we attach 5-dimensional cell to the 3-dimensional using, again, more space, and so on. So we have these things. And so we have proved the well-known Whitehead-Chang theorem that every polyhedron from CW3 having 3 cells on 3 levels, yeah, is a bouquet of sphere, suspended more atoms, and chunk atoms. One can prove that such a decomposition is unique, which is non-trivial and can be wrong in more complicated cases. And I must know that C eta is just a suspended complex plane, and C2 eta, this one, where R equals 1, is the double suspended real projective space. The case of 4 levels is essentially more complicated. Here we also set M equal to 1. Then B is isomorphic to CW2. So in decomposables are spheres and more spaces. A is also has only 2 levels. Yeah, so in decomposables are spheres and more spaces also. And one can calculate the values of, yeah, here they are. I will not explain this table, but it doesn't matter. It is convenient to organize the matrices describing morphism from A to B as in the following table. Yeah, you see most of them are the direct sums. This is Z2 plus Z2, or even this one. Yeah, so we split them. For instance, what does it mean, these 2? It corresponds to more space with degree 4. Yeah, 3 correspond to more space of degree 3, both here and here. and these arrows show that we can add columns. That 2 means that it is the values are from the cyclic group of order 2, the infinity from the infinite cyclic group. Yeah. And these arrows show that we can add columns from left to right and rows from bottom to up. The classifications of such matrices under isomorphism is a sort of matrix problem called bunch of chains. Such problems were considered by Nazarova, Roit, and Bondarenko, and they proposed the way to describe a suitable answer. In our case, this answer, that is a description of items from CW4, happens to be rather regular and easily presented by the corresponding gluing diagrams. These diagrams are of two sorts, called strings and bands. And there are also 3 types of strings, usual and decorated. And usual strings are of this sort. So we have more atoms, and they are glued like this. Yeah, and it can stop at any point. We can start from here and stop here, and so on. And decorated strings also are these gluing and plus some decoration, either this one, this is double hop map, or this one. Yeah, we add one more atom inside. And what are bands? Bands are a bit more complicated. First of all, we have several cells at each level. Yeah, not one, but several. Yeah, and then we have this usual gluing. The first, what are these? The first cell up to the first cell down, the second to the second, the third to the third. But we have an extra gluing, this one long gluing, which is ruled by a Frobenius matrix. Yeah, for instance, if we have this Frobenius matrix, then this attachment is given like this: the first cell to the second to the third, and the third to the union of first and third. Okay. This description was done by Howes and Hennes, then by Baus and myself, but we used it was using quite different and more refined technique. For if we take bigger n, the structure becomes awfully complicated. As they say in the representation theory, it becomes wild. It means that for any finitely generated algebra over the field of 2 elements, there is a functor from lambda models to these categories that maps indecomposable models to indecomposable polyhedra, non-isomorphic models to non-isomorphic polyhedra. Obviously, it implies that there can be no hope for more or less transparent description of atoms in this case. So we must use something more. Yeah. Fortunately, there is another case when we can do more. It is when we consider torsion-free polyhedra. That means the polyhedra such that all their integral homology groups are torsion-free. What does it simplifies the things? First of all, there can be no Moore fragments in such polyhedra because each Moore fragment gives torsion. Yeah. Another condition, if we construct X as the cone of a map, where B stops at the level n plus m and the A starts from the level n plus m, yeah, then F must induce the 0 map on this overlapping dimension in homologies. Actually, it is enough, and we have the following theorem. Let's see F and D. This is the subcategory consisting of torsion-free polyhedra. Against CFM, that means just the same. Again, we choose some M, consider B and A, like before. And then we take not the whole module of morphisms, but it's a model consisting of such morphism that it induces 0 map on the overlapping dimension. And again, we define I and J, the ideals as before. Then we have the same equivalence. But in this case, we have some advantage. We had that J squared is 0, but in this case, I squared is also 0. And we have a one-to-one correspondence between isomorphism classes of torsion-free polyhedra and isomorphic classes of these objects of bimodal category. For instance, in CW4, the only torsion-free atom is the double chunk atom, which is like this. It's the only one which doesn't include more fragments. And if we consider CF5, take M3, then B will have 4 levels. And A will have only 1 level, so it consists of spheres. So B consists of spheres, chunk spaces, and double chunk space atoms. And we have these values for this our bimodal. And applying automorphism, one can classify all possible atoms. I will present their gluing diagrams. They are like this. So we have this chunk and double chunk atoms, and we glue the spheres and these atoms like this, using this long. What does V means? You see, here we have the maps from the 7-dimensional sphere from 8-dimensional sphere to 5-dimensional sphere. The corresponding stable homotopy group has order 24. So V shows the order of this gluing. Again, no. A new feature in this case is that the decomposition of a polyhedra into a bouquet of in the composables is no more unique. For instance, if we have these atoms A3 and A9 and glue them with the 5-dimensional sphere, they become isomorphic. They become homotopy equivalent. This is the same for n equals 6. They are also, in CF7, there are also infinitely many, finitely many atoms. But in SF, if we take n equals 7, then there will be infinitely many torsion-free atoms. They can also be described using the results of bunches of chains of strings and bands. But these strings and bands are more complicated than before. They're not so regular. For instance, this is an example of a string. You see we have this chunk and double chunk atoms glued by some maps. Again, this it shows the order of this map. So you see that they are not so regular as for CW4. And if n is bigger than 7, the category CFN becomes valid. And so to study the corresponding polyhedra, we must invent new apparatus. And at the moment, I don't have such apparatus. Okay, so I think I must stop now. Thank you very much, especially for your patience.
Thank you, Professor, for so impressive talk. You still have some minutes, but in case of your finishing earlier, so please contribute any comment or questions, please.